Welcome to everyone who is joining us via the recording. So we are just kind of doing a midterm review to make sure you guys are all in a good place for the midterm.
Yes.
Do you have any questions?
Straight out of the gate. All right. Yeah, they're like, is this kind of just like kind of free form, like whatever
Yep.
whatever we're struggling with, we'll take a look at.
Basically.
Okay. Yeah, there's a couple. I was doing some of the practice exams and gosh, let me pull one. So one of the ones that kind of gave me some issues doing finding the limit with trigonometric functions.
Okay.
It's one of them. There's a couple things.
Yeah. I hit some issues with some of those as well. In that I could not figure out how to solve them without using material from other courses. So I have been trying to figure that out for off and on for the last like 2 hours.
Sure.
And I do not have a good answer for that. I think I know which problem it is that you're having problems with.
I pulled the first one. Like I mean, I wouldn't like the trigonometric functions make whatever problem I'm trying to solve a little bit more challenging.
Yeah.
I wouldn't put this one at the top of the list, but it was the first one I pulled.
Okay. Let me open up all of the practice exams real fast.
Okay.
So give me like 30 seconds to crack these open. Which practice exam is it?
So this one I have here is from example B, or sample B.
Okay, sample B. All right, and which one is it?
So this one's number 7.
Okay. Oh, okay. So this is not one of the limit problems. This is for sample B, number 7. I have on which intervals of the graph is the graph f of x is equal to 2x to the 5/3 minus 5x to the 2/3 concave down.
Oh, that is not the one I'm looking at all.
Okay.
Actually, let me see if number 7's a different one. I don't have that for exam 1 sample B.
Oh, I'm looking at exam 2 sample B, yeah.
Oh, God. Oh,
I'm looking at the entire wrong. I was like, why is there linearizations on this? Okay, let me fix this. I'm so sorry. Oh, Lordy. Sorry. Okay, let me fix this.
And I know you're recording for multiple people. I will give you the disclaimer up front that I will maybe bounce in the middle of this because I scheduled mine at 6:30.
Oh, so, yeah, that's totally good.
And I figured do some review, have it fresh, go into it. Got it.
You just leave whenever you need to. So if you need to stop and take a minute, like before you start, don't feel like you need to work with me all the way up to 6:30. So you just tell me whenever you're done. And
yeah, and I know you do it for everyone else, but just so that you're not talking to a phantom. Me.
Well, thanks for letting me know before you leave.
Sure. Yeah. No. Yeah. I wasn't just.
Okay.
Rude.
Okay. Yes. I see number 7.
Okay. like the first thing that like if I can just like
walk me through your thought process.
Yeah, if I just talk through. So I know that if the denominator is going to be 0, we try to factor it in a way so that it's not 0. First thoughts when looking at this is I'm not sure how we're going to. It's h is okay. H is approaching 0. Yeah, I'm not sure how. Like, so we have h in the denominator. That's I can't get past that hurdle. I suppose.
Yeah. Okay. So, well, first of all, it's not necessarily bad to have h in the denominator, right? Because if I have something even just as simple as if I have something like 1 over 0, if I am approaching 1 over approaching 0, if I've got this as a limit, what am I going to end up? If I'm dividing 1 by something that's approaching 0, I'm going to end up with infinity, right?
Oh, is that where we get into like plus 0 or minus 0? Like,
yeah,
in terms of which direction we're hitting 0 from.
So that in particular, the directionality depends on the directionality matters in some cases because you'll have a graph that looks like this, where you'll have something as x approaches like -3 here from the left, it goes all the way up, and if x is approaching -3 from the right, it goes all the way down. And so it's like a discontinuity within the function, right?
Sure. Right.
Because x from the left, or the limit as x approaches -3, we'll call this, from the left is not equal to when it approaches it from the right. But in this case, while we should consider that, it's like not very explicitly stated.
Sure.
So first things first, let's see what happens when we just substitute in h goes to 0.
Okay.
Right?
Sure.
So h goes to 0 here. And we end up with cos of pi over 3 minus cos, here, I'm going to rewrite this.
All right.
So h goes to 0. So this is approaching cos pi over 3 minus cos pi over 3, which is approaching 0.
Sure, right.
That's kind of how I like flow my thoughts when I'm doing limits. So the denominator is going to approach 0, which is again approaching 0. So I end up with something of the form 0 over 0, which is not something that you know how to solve.
Right.
Which means that for this class, we're going to need to do something else that will make this solvable.
Right.
And I have been trying to do that within the confines of this class for a while now, and
well, I guess, like, I mean, I did print out the solutions along with it.
Yeah.
My goal was
Let's take a look at that.
Yeah, like I would go through the test and then circle back to the ones I couldn't do, look at how they did it, and then a couple days later, I'd try the test again, not having remembered the answers, and like it's still hits that wall, like I don't remember.
Yeah,
they said it. So they said it. They take the derivative of pi over 3. Oh, because
they.
Oh yeah. So.
I'm so sorry that I'm not able to like adequately answer this question.
No, that's all right.
I've been kind of freaking out over this for the last few hours.
Sure.
Especially since our discussion last week when Hayden mentioned L'Hopital's rule, which was for that type of problem, not quite the right approach. but for this problem would be the right approach. But you guys don't know how to do that yet.
Right, and it does say in the practice exam not to use, it did actually state that for one of these problems to not use that rule.
So,
but I guess looking at this now, I think I get why they're going step by step, because the way that this is set up in like the definition of the derivative of a function, right?
yes,
Like that's how the structure of it is set up, and so that's why. Okay,
yeah,
I kind of get that now. If this were not set up the way it was, you couldn't just take the derivative of pi over 3 and figure it out that way.
Yeah. So that being said, I think what they want you to do here is, instead of finding this limit, they say that this is going to be the limit of f prime of pi over 3, right?
Right, that is.
So it just like it. Reading through this whole like answer sheet is, I don't know. I'm not a huge fan of how this got set up.
Well, like it does. Like I don't know if if it's for this reason that you feel that way, but when seeing some of these step by steps, it almost seems like it jumps. It jumps a step or two, like, and you're kind of like, I'm looking at the solution and I'm trying to figure out the solution in terms of each step to each step, which I kind of had to do just now with this one.
So, walk me through this. If the way that we're going to solve this is by taking the limit like normally, right? So we're going to try to take this algebraically instead of taking the limit by hand through this limit. We're finding the derivative algebraically instead of finding the derivative by taking this limit by hand. What is the original function? I know it says it right on there, but just like walk me through it anyway.
I guess the original function would be sine. Wait, we're not taking the derivative. Sine pi over 3.
Not quite, because remember, sorry.
Would it be f of x equals cosine of x, and x equals pi over 3?
Yes. So, if you remember when we're setting up the like finding a derivative by hand, we'll have f prime of x is equal to f of x plus h minus f of x over h, right? That's the equation. Pretty sure. So in this case, f of x is going to be just like cosine of pi over 3. So we know that our f of x function is cos x, and our x is going to be pi over 3. So we've established that based on what we know about the definition of the derivative. That being said, now we can just go ahead and solve the problem like using algebra. So we have f prime of x. If f of x is cos x, then what is f prime of x?
Negative sign.
Negative sign.
So then we would end up finding f prime of pi over 3, which is equal to negative sine of pi over 3, which is equal to 3 over 2.
Sure.
So if I said that this limit is equal to f prime of pi over 3, and I said that f prime of pi over 3 is equal to root 3 over 2, negative root 3 over 2, then all of these should be the same. They should all be equal to one another. And that's how they want you to solve this problem, I guess. So the big important key here was to recognize that this is the definition of a limit.
That seems to be that first hurdle.
Yeah. So that is number 7.
That clears that up.
how about, is there another problem that you want to go over?
The last one I did, for me personally, finding the change in height of the upside down cone.
Mm-hmm. Do you have an
was one-
example on one of these exams?
Yeah, it's I think it's in the first one. Sample A, and it's the last. Yeah, it's the last problem, 17.
Okay, so A, problem 17. So water is flowing out at a rate of, oh, is this a follow-up question? No, it's not. Water is flowing out at a rate of 50 meters cubed per minute from a conical reservoir, vertex down, of a base radius 15 meters and a height 6 meters. At what rate is the water level changing when the water is 5 meters deep? So let's sketch this out and let's figure out what we know and what we need.
Sure.
So I know I've got a cone. So there's my cone. I know that I have water in my cone, and I know that it is flowing out. So I know that the height of my water is going to be decreasing. So let's break this down into what I have and what I want. What information is given to me?
So we have the change in volume
Mm-hmm.
of dV dt, which is negative 50 meters cubed a minute. We have the base radius at the top, which is 15, and the height, which is 6. Yeah.
So what am I going to do with the base radius and the height?
So, because this is fresh in my mind, I do recall what we're doing since we have like triangles with the base radius and base height and the radius and height of the water that's in there. We can set them equal to each other relationally.
Yeah. So the relationship of the radius to the height is going to be the same for the water and for the base radius and the height. So what do we want to put this in terms of? Am I solving for R in terms of H, or am I solving for H in terms of R?
Well, so we're trying to solve for height, right? So that's why we would want to, we want to, in this instance, solve for R. We want to see what R is.
Yes. So R is going to be equal to 15H over 6, right? So I can go ahead and say that I have this equation, which is V is equal to 1/3 pi R squared H. And now I can put this all in terms of H. Okay. So what is that going to be? That's going to be 1/3 pi. And that's 15 squared is what?
So I do remember for this example, I don't know if this will help. They did simplify 15 over 6 to 5 over 2.
Yeah, we're just going to be simplifying the whole thing anyway. But
Sure.
yeah.
Yeah, and it's because, like, I mean, since there's no calculators involved,
Yeah, you're right.
I was like, man, I'm gonna have to do like things like 25 times 15 and like do like little side notes for just minor things.
Okay. So this is going to simplify out into 25 pi h cubed over 12. And that is that. So I'm going to rewrite this equation up here. And then erase some of this work so I don't have to look at it all the time. So I have v of h is equal to 25 over 12 pi h cubed. Okay. So, are we good with that up until here?
I believe so, yes.
Okay. So that gives us the h. What is it that we're looking for in this problem? What is our goal for solving this problem?
Well, so I guess we want dh dt, right? Okay.
Because we're looking at the change in height. Okay. So, the final question of what we have is at what point are we going to be doing this? We're trying to find this when the rate of the water level, what is the water level changing? Yeah, so when the water is 5 meters deep.
Right.
So when h is equal to 5. Okay. So, what's my next step? I've established what I have. I've established what I want. I've got the equation that I think I can use to get it. Where am I going next?
So from here, wouldn't we just plug in 5 for the height, while also, or I don't know. Okay, did you first? Okay, and then plug in 5.
Yeah, so first things first, we need to make sure that we take the derivative because we need to be looking at this, we need to implicitly differentiate so that we're looking at this in terms of rate of change. Because if we want dh dt, we don't have it in this equation.
Sure.
There's no way that I can use what's here to solve for dh dt without implicitly differentiating. So we're going to end up with dv dt is equal to what?
So I think this was like, I follow when I answered this, when I followed the explanation, but I kind of got tripped up where it seems that the derivative is only being applied to h and not the rest.
75. Would it be 75 over 12 pi u squared? And then after that, you plug in your 5 for h.
Yep, we're only missing one thing here. And this is dh dt. Yeah. So let's break this down just a little bit more. That is exactly right, answer-wise. But remember what we're doing here is we're dealing with a chain rule problem, right? So we're finding dv dh and then multiplying it by dh dt. If I have the function v of h of t, so I have a function within a function, the way that I solve this is by saying v is a function of h, v prime of h is whatever v prime of h is. I have h as a function of t, and then I have h prime of t, And then the way that I find this derivative is by saying v prime of h times h prime, right?
Mm-hmm.
So that's what the chain rule looks like. And we're familiar with that. We use that to find derivatives. And what that is exactly exactly what I have over here, right? This is dv dh, and this is dh dt. It's just written in Leibniz notation.
Right.
So I just took the chain rule to find out what was going on here, because I've got a function within a function. So then my next step is to say, if I have the function v of h is equal to 25 over 12 pi h cubed, I need to take the derivative of that, v prime of h, which is equal to dv dh, which is equal to, I have only one variable here, so I can use the power rule. So it'll be 3 times 25 over 12 times pi times h squared. Because this is 3 minus 1, and then I bring the 3 down. Is all of this familiar? We're all on the same page? Okay. So dv dt is equal to 75 pi over 12 h squared dh dt. And again, it's imperative that dh dt sticks around. It's often what's forgot when implicitly differentiating, but we need to have it because it's what we're solving for.
Sure.
So if we forget to include the dh dt, then we don't have what we're actually solving for. So now we know we have dv dt, and we know we have h, because we said that this is when h is equal to 5. We can use that to find what dh dt is. So I'm going to rewrite this. I have negative 50 meters cubed per minute is equal to 75 pi over 12. H squared is going to be what?
25.
The height of the wire, which would be 5 squared, is 25.
What are my units?
Meters?
Meters squared per second?
Not per second. We just have height, right?
Okay.
So if h is just 5 meters, then I just square it to be 25 meters squared.
Got it.
Okay. And then that is multiplied by dh dt. So what I'm going to do is I'm going to multiply both sides by 12 over 75 pi. So I'm going to get rid of that. And I'm going to end up with, this is going to be negative 12 times 50 over 75 pi. And I can factor out a 25 here, right? So I can call that 3 and I can call that 2.
Yep.
So this is going to be negative 24 over 3 pi. I can get rid of that 3 if I call this an 8. Right? So I've got negative 8 over pi. And then what units do I have here for all of this work here?
Meters cubed per minute.
I'm still at meters cubed per minute. I didn't move any units around. So give me just a second. I'm going to rewrite this so that I can try to fit this all on one page. One sec, okay. So we said I had negative 8 over pi meters cubed per minute is equal to, and now I'm looking at 25 meters squared, dh dt. So I'm going to divide both sides by 25 meters squared. So what is dh dt?
So -8 over 25 pi meters a minute.
All right. Okay.
Okay.
Does this answer make sense?
Yes.
What two things indicate that it makes sense? There's two things about this answer that I'm like kind of looking for that tell me that it's a good answer.
So no, the negative is key there because water is leaving.
Mm-hmm. So the height is decreasing over time.
Sure. Yeah.
The other thing that would tell me that I'm doing well is my units. I have a change in height over a change in time. And so that means that my units are in order and I have an answer that makes sense.
Yes.
If I ended up with meters squared per minute, then I would have an issue somewhere.
Yeah.
So just keep track of your units, make sure that everything's in order.
All right.
Okay. Other questions?
Yeah, I can keep going.
I didn't do the practice exam yet, so.
Okay. Well, if you have any other questions from like the book or something, of course, feel free.
I don't want to hog all the all the questions.
No, go for it. Yeah, I just look for different problems and just seeing them solved or helping solve them is usually
Sure
what helps me out.
There's two I have off the top of my head right now. One is from sample B, number 6.
Okay.
This one is a little hard for me to grasp when the with regards to the constant C.
Mm-hmm. Okay. Give me a quick sec to look at this.
Sure.
Okay. So, okay. This one. What I'm going to refer back to for this problem, you understand the concept of this like bracketed function, right?
Right. For like if x equals whatever amount, it's this function. If x equals a different amount, you use this.
Yeah. So if we're under 0, then we're looking at this top one. And then if we're equal to or over 0, we're looking at this bottom function. So what I'm going to throw back to is the definitions of continuity, right? Because we're asked to figure out, our goal is to find out what is C such that f of x is continuous for all numbers, right?
Mm-hmm.
So our goal is to make sure that we have a continuous function. So we have 3 rules for determining continuity. Do you remember what they are?
No.
Okay. They're very straightforward. First of all, f of a exists. Second of all, I think it is the limit. This is the limit of x goes to a of f of x exists.
Okay.
And the limit of x goes to a of f of x is equal to f of a. Right?
Okay.
So basically everything exists and they equal one another. So if you kind of want to throw back, we had problems where this was not the case. We had problems where we had, if we talked like earlier, when we had like an asymptote, right?
Mm-hmm.
If I had a function that looked like that, then here, if we call this x is equal to -3, right? Then the limit, well, the limit wouldn't exist in this case either. But if we had a limit that looked like this, the limit would exist, and the limit would be positive infinity, but f of a itself would not exist. So we have like a moment of discontinuity, right?
Sure. Right.
And then another instance would be if we had like a gap taken out of a function. So if we had something and then there was like a hole in the function and it was filled. So f of a might exist. The limit as f approaches, or of f of x as x approaches a would exist, but they're not the same in this instance. So we need all three of these things to be true if we will have a continuous function. So we're just going to set out to prove that this function is continuous. And that is really all we need to do. And we need to just figure out when that's the case, basically. Sure. Whenever C is. Okay, so the way that we should set this up is we have one number where the limit needs to be, where the limit's going to get a little wonky, right? In that we need to make sure that it is continuous as f approaches 0 from the left and from the right. Because if it approaches from the left, we're using this function, and if it approaches from the right, we're using this function.
Okay.
Right? So
yes.
How am I going to set this up?
Well, when you explain it that way, I feel that I would, like you want to set up two limit functions, right? So if you do the limit of x as it approaches 0 from the left, sine cx over 3x.
And what is this equal to? If we just flash back to our rules of continuity.
Oh. A?
Yeah, but in this case, our A is 0, so this is f of 0.
Oh, right, okay.
Okay. So,
okay.
Then if f is the goal here is to say that this is equal to f of 0, and so is this other limit, right?
Yes.
Because once again, we have x approaching 0, and we're trying to prove that the limit exists. We just have to do it twice because we're approaching it from two different sides.
Right.
So this will be the other limit, and they're equal to one another. Does that make sense?
Yes. Yeah, I follow.
So we need to make sure that they're equal to one another in order to have this be the case. Okay. So as x approaches 0 from the right, what is the limit equal to?
1.
Yep. So we just need to find an instance where this limit, as x approaches 0, sine x over 3x is equal to 1. We need a C where this is.
Oh. Okay. I see it now.
Yep. So, yeah.
So in this case, it would be 3.
Yes.
Right. Okay.
So if C is equal to 3, then the limit as x approaches 0 is of sine 3x over 3x is equal to 1. Yeah.
That clicks a little bit more now.
Okay. What was that?
Oh, I don't know.
Oh.
I know I didn't say anything. I was breathing.
Oh, sorry.
That's all right. No.
Okay. So that's what I have to say about this.
That's good. That saying them equal to each other. That's you're kind of just trying to balance both sides.
We just need to make sure that they're equal so that they're continuous. Or they're continuous.
Where did
so
that
they're equal.
C equals 3 come from?
Okay. Now this is my issue with this problem. I'm not sure if you were here earlier when I said that I spent a hot minute trying to figure out exactly how they wanted you to solve this problem. Did you guys use small angle approximations to solve limits?
No.
I hope not because.
Okay. Okay.
Does not ring a bell.
That's. I mean, I didn't think it would, but I don't know how they would want you to solve this without small angle approximations or another like method that they haven't covered yet. And I spent a while trying to figure out how exactly they wanted you to solve this. The best I've got is there are a couple instances in the answer keys when there's a very like jumpy answer where they basically say that if you're taking the limit as x goes to 0 of sine x over x, it is equal to 1.
Okay, so that
Which
I was
is
gonna.
true.
So yeah, so that's what I was going to say. So, yeah, I didn't recall learning that, and then I think through looking at examples of this, that was brought to my attention that is a rule. Like that is like
there's a reason this is the case. You just don't know it yet. And that is very frustrating to me. Because I don't know why they would give you. Yeah, I don't know why they would give you this.
And I'll tell you what too. There's I don't have it here. I can't, but I do remember doing an example where when they, I think it was one of these, where when they showed the process of how to get the answer, what they did is multiply the numerator and the denominator by like 2, because doing that would have set it would have set sine
I
x.
saw that. I know exactly. I know exactly what problem you're talking about, and I don't
like it.
So
yeah, I saw that. I'm like, oh, I'm gonna have to remember that is a rule.
I spent a hot while trying to figure out why exactly they have included these problems, and I don't know why. So they always seem to do it in this form though, of the sine x over x. So if you see something like that, try to think of one.
Got it.
And that's what I can tell you about this right now.
Got it. Okay. I'll just try and log that in my RAM of my head and. Okay.
So
God, so it wasn't just me. So I'm like looking at it, I'm like, I really don't remember that being a thing.
Yeah.
Yeah, I mean, I don't remember that either. When you said 3, I was like, how did you get that?
I know.
And that's because I was remembering that problem. I'm like, oh, we just make sine 3x over 3x, and that's
how
1.
It was on the example. It's example exam C, problem 10, and that's the one. It just
Oh, yeah.
I spent probably about a half an hour trying to do this problem without,
that's the
like,
one.
with the tools that you guys have. And you need small angle approximations or you need L'Hopital tool. And I don't know what to tell you guys other than try to get it in the form of sine x over x and then just say that the limit as it approaches 0 is going to be equal to 1.
That's fine. That's what they want. I can,
Okay.
that's what they want.
Yeah.
I can try and remember that.
That being
good.
said,
that ticks one off that list.
Always make sure that you don't panic. And if you see something like this, if you see something with a ton of trig functions and you're like, oh gosh, this is like something that's really complicated and it's going to be like 0 divided by 0 or something like that. If I just plug it in and I can't simplify it, what do I do? Make sure that your limit is actually going to 0.
Got it.
Because if this is going to like 4 or something, you're fine.
Right, we don't have to.
Yeah,
right, we don't have
to worry.
Okay.
The moment you worry about something like this, when you have something of the form 0 over 0, is when x is actually going to 0, and you end up with this in the red here.
Got it.
Don't worry about it if it's like complicated, but it's going to like 4 or something, because you can handle that. That's fine. It's the it's the other ones. So that being said, so we'll have the limit as x approaches 0 from the left of the sine c of x over 3x. And the important thing to recognize here is you're going to want c to equal 3. And I can walk through exactly why that is if you want to see it, but I don't think it's good for you to complicate your, I don't know. It's just introducing new material.
It might hurt.
Right before the exam. And I don't think that's good.
Yeah, it might hurt. So, it might hurt more than help.
Yeah.
I'll learn it like tomorrow. That's fine.
But today I think is good to focus on what exactly.
Sure.
So.
It's fine.
That's that. Don't ask me to solve C10 because I won't do it. C10. I can't solve that problem in a way that you guys. I don't know what they want me to do.
No, I mean I once again like I can look at how they did it on here and just hope that if I get a problem, it's set up very similar to it, but. I mean, I'll cross that bridge, I guess, when I get to it. I do. Cool. Oh no, sorry. Go ahead.
I had trouble. Is there a problem on the example that was like on the homework? The one that I have is you're flying a kite 100 meters above the ground. The string is getting let out at 8 feet per second. And then you're supposed to find the rate of the angle getting changed when the string is, I think, 200 feet out.
Okay. Do you want to read me that exact problem and we can do it, or I can scroll through the exams and try to find something that's similar? But I think what you really want is that angle problem. Am I right? You want something that deals with that angle?
Yes, just an angle problem. I usually have trouble with the whole sine and cosine, trying to figure that out of the rate of change of an angle.
Yeah, I also get stressed whenever an angle pops up.
Last week, I think last week we dealt with that one, and that was
we had
equally a challenge.
Long problem, I think, last week.
Oh my gosh, yeah, that was insane. And it may have been that exact problem too.
Yeah, it might have been. So hang on. Okay. So in the book, I'm looking in section 2.8, and I'm going to do problem 30. So a kite, is this the exact same problem? I don't think it is.
Yep. I guess we'll...
It might be. We'll find out, I guess, as we do it. So a kite is 100 feet above the ground. I think it is the exact same problem. LOL. 100 feet above the ground, moving horizontally, right? So here is our kite. It's going to be black, and it's going to be very awkwardly shaped. And here's our string for our kite. Okay, so we just kind of sketched this out, right? What information do we have? I'm just reading this problem. I have that it is 100 feet above the ground. I have that it is moving horizontally at a speed of 8 feet per second. I have that we're trying to find this when 200 feet of string has been let loose. And we want to find the angle between the string and the horizontal. So which angle would that be? This one, number 1, number 2, or number 3?
Number 3.
Yep. So I'm looking for angle number.
I usually draw my triangle reverse from the kite to the ground and over to the person holding it.
Oh, like this?
Yes.
Something like that? Okay. We can do that for sure. It's the same, you know, concept. So we have the ground. Oh, I just picked a straight line tool. That's fine, actually. Then I get straight lines. Cool. If I can draw them. Okay. So here's my kite. I'm going to label all of these. This is going to be, the reason I drew it the way that I did with that up top is that I kind of had it visually like moving in a horizontal at 100 feet because the kite is moving like this, right?
Yes.
Along that dotted line, and it's never going up or down. So I might actually revert it to the other way that I had drawn it, just for clarity's sake, if that's okay.
Yeah.
Because if you draw it like this, it's letting me say that I have a string, like I can see the string, and I can see the line where it's moving above the ground. So I could like extend this line, and it would like show if it's not going to behave strangely. I could extend this. Yeah, I could extend this line, and I could see that there's like a line on which this is moving, and I can like I can clearly see that my y is not changing. Basically, is what I'm trying to get out of this. And I am going to call this y, and I'm going to say that it equals 100 feet, and I'm going to say that that's constant. And then I'm going to call this z. And this is my string length, right?
Yes.
Z is going to be my string length. And then I'm going to have x right here. And what I know is dx dt is equal to 8 feet per second. And I know that because our horizontal is changing at a rate of 8 feet per second. And it's moving this direction. It's getting longer. So what does that mean? It means that our z is going to have to get longer too. So that kind of sets up where we're looking at what we're looking at, right? And then here is my angle, which I'm going to call theta, right?
Yes.
Write it clearly. And this is the angle between my horizontal and my string. So I can see that as this triangle gets longer, as my x increases, my theta gets smaller, right? So my theta is decreasing, which is consistent with what the problem has asked me. So This is the information that I initially have. What is it that I want from this problem?
You want the rate of change. You want theta over time.
Yes, I want to find the derivative of theta with respect to time. How is theta changing with respect to time? We know it's decreasing, but how much is it decreasing by per second, basically, is like what we want our answer to be. So this is what we want. So we need to get ourselves an equation that we can use to find this out. Okay, so
oh, I remember.
Yeah. So what is our next step? We're going to have to set this problem up.
Do we want to actually set up, like, kind of go from the end to the beginning? Like, we want to set up how we want to solve it and then find the things we don't have?
That's exactly how I approach these problems.
Okay.
I figure out what equation am I overarchingly going to have to solve.
Yeah.
And then I go from there.
Got it.
So the overarching equation would be theta equals now you got me. It's like
yep. Okay, so the easiest way to find theta
would it be inverse of sine?
We could do an inverse of sine, but remember on the exam you're not going to have a calculator
in here when I'm studying right now, but
so what we're going to do instead is, if we have something that looks like this, right? We're just going to say that sine theta is equal to opposite over hypotenuse. Opposite?
Yes.
100 feet over hypotenuse. Z. Right? And I'm actually going to rewrite this so that it's 100 d to the negative 1, because that's how I live my life. It's just easier to work with. And this is going to be the equation that I'm going to use, because if I take the derivative of this, I get to implicitly differentiate both sides with respect to t. So this will be d, it's a little bit harder to like state like explicitly. If the function f of, if this is a function f of theta of t is equal to sine theta of t, right? Then the derivative of this would be df d theta dt, in which case we would need to find the derivative of sine theta and multiply that by theta d theta dt. Does that make sense? So we're implicitly differentiating with the assumption that theta and z are both functions of time, which they are, because both theta and z are changing with respect to time.
It'll be cosine of theta equals...
Cosine of theta what?
Oh, times d theta over dt.
Mm-hmm. We cannot forget that part of the implicit differentiation. I'm actually going to write this up here.
Equals 100 z to the negative z squared dz over dt.
Yep. So it'll be negative 100. Don't forget that minus sign up front. And then, yep, negative, or z to the negative 2, dz dt. Precisely. So that is the equation that we're going to be working off of. All right. All right. So we rearrange a little bit, and we can say that this is just divided by cosine of theta. So what's my next step? I now have an equation where I have my d theta dt, but I'm missing some things. I'm missing dz dt, don't have that. I have z. This is going to equal z. I have 200 feet of string. And I'm also missing my theta at that time, right?
Yes.
So let's find either dz dt or theta, and
That would
start
be
filling this out.
Pythagorean theorem, right?
Yep. So tell me what I'm going to do.
Well, you have y squared plus x squared equals z squared, and you have to find the change of rate. So differentiate that. 2y and dy times dy over dt, then x, or 2x times dx over dt, and then z, or 2z over, 2z times dz over dt.
Exactly.
I think it's just simple. Isn't it easier just take all the 2's out, and at the same time, since y doesn't change, so dy dt would be 0. So you have dx dt.
Great. Awesome. That's exactly what we're going for. So dz dt is going to be equal to dx dt times x times 1 over z. We know dx dt is going to be 8 feet per second. What is x going to be?
Ooh, that's just the plain Pythagorean theorem. If you do 200 squared minus 100 squared equals x, or the square root of all of that equals x. So square root of that.
So this is going to be the square root of 30,000, which is 100 root 3, right? Because this is 10,000 times 3.
Yeah.
So yeah, what I would say is this is 10,000 times 3. And I can say that I can split up the root, so it'll be root 10,000 times root 3, and the root of 10,000 is equal to 100.
Okay.
And that's how I would break that down. So we have 100 root 3 is equal to x. And then what are my units for x?
That would be feet.
And then z is 200, we said, and then
Yes.
feet, also in feet. So dz dt is equal to 8 times 100 root 3. So I'm going to just call that 800 root 3 feet per second. And this is 200 in the denominator. I'm going to get rid of that, and I'm going to just call this 4. So this is 4 root 3.
How did you get that, the 1 over the z?
I divided by z, both sides.
Okay, you move the z from the right to the left and then flip. All right, yeah. Okay.
So it could be times 1 over z, both sides.
Yes.
I could have waited to do that if I wanted to, but I just thought I would solve for dz dt. Okay, so we've done all of that. Great work with that implicit differentiation. I'm going to go back up here, and I'm going to say that dz dt is equal to 4 root 3. And what are my units?
Feet per second.
Exactly, feet per second. Okay. All right. What is the last thing that I need to find?
The angle. Which.
So the way that I would do this is let's see. I would probably just take the sign at the certain moment. So I would say that sine theta is equal to opposite over hypotenuse, which is 100 over 200, which is 1/2. And this is just one of those like identities that you're going to want to know, right?
Mm-hmm.
Pi over 3?
I think it's pi over 6. Because this is
Yes.
a 3060.
I always get them too confused.
Yeah, me too. So if we have like a 3060-90, right, then this is pi over 6, and it'll be hypotenuse, that's 2x. This is going to be x, and this is, I think, root 3x height. I think that's what a 3060-90 looks like. And so this tiny angle is going to be 30 degrees or pi over 6. So we can use that to say that theta is equal to pi over 6. I'm going to put that right here. Theta is equal to pi over 6. Okie doke. All right. Another thing that we could do there is instead of we could do whatever cos theta is. So cos theta is equal to the adjacent, which would be x over the hypotenuse. And if we're doing it at this specific moment in time, right, then that would be x, which is 100 root 3, right,
Yes.
over 200. So this would be root 3 over 2. Yeah. And then I wouldn't have to deal with using this. So there were two options there. I could have immediately found the angle through the 3060-90, or I could have just done this. And I would end up with the cosine of theta is equal to root 3 over 2. Okay.
Okay.
So we put it together now. D theta, I'm going to put this up a little bit. D theta dt is equal to negative 100 times z to the negative 2, where z is going to be equal to 200 feet, times dz dt, which is going to be 4 root 3 feet per second, all over the cos theta, which is going to be root 3 over 2. So I'm actually going to bump down my z. I'm going to take this and put it down here and say that this is times 200 feet squared. So I'm going to have this negative 2, and I'm going to turn it into a square down there. So this is going to simplify into negative 100, or negative 400, excuse me. 400 root 3 feet per second. And then I have root 3 over 2, and I can jump up with that 2, or I can just say that this is 40,000 feet squared. So I can get rid of that, and I can get one of the feet from there and one of the feet from there. I'm not missing any units, am I? I don't think so. And then I can divide 40,000 by 2 and make this 20,000. And I can get rid of those root 3's. They're going to cancel. So I'm going to end up with negative 400 over 20,000. I'm going to get rid of those 2 zeros. So negative 4 over 200, which is negative 2 over 100, which is negative 1 over 50. My units haven't worked out. Where did my units go wrong? Oh, I don't have units for my cos theta. Do I need units for my cos theta? This is the right answer. Negative 1 over 50.
Radians per something.
Yeah, my answer is negative 1 over 50 radians per second. It's good I did this because this is in radians. So I end up with radians here.
Mm-hmm.
But I don't exactly know how that's going to transfer. Can we just fudge the units on this one? I'm not sure how the units are going to behave with the trig function. And I know this is right because I have my notes from last time. And
unfortunately, they get, like, I think with the multiple choice, they're not evil in the sense of, like, some are not squared and some are cubed and some are like, it's, I think they're all like squared, they're all the same number of units.
It's just generally like a really good handy rule. I just, right now, I'm not sure where that extra foot is going because I have 1 extra foot. Right?
So the feet
I have
squared.
Yeah, I
Wouldn't
have.
it be 100 feet?
Oh, yeah, negative 100. Well, isn't it 100?
Negative 100.
Oh.
That isn't quite right because I think. Oh, it might be because we got this from over
From
here.
the height.
Yeah, so we just lost a foot there. Okay, so if that is in feet, then the feet will cancel, and I end up with blank per second, which is fine because this is radians.
Yeah.
And the radians are going to be wonky anyway. But okay, so we found the missing feet.
And I'm actually gonna head out right now.
Okay.
Sorry to interrupt. Good.
For sure.
Stopping place.
Good luck.
Thank you.
Yeah, you got this. You're prepared.
As long as this was not a good problem to like go into practice going into the. I'm hoping not for a kite flying problem.
Well, if there is a kite flying problem, you are going to be so prepared.
Sure. Yeah. No. True. I just
you'll have just done it.
Yeah. Right. That's going to be the circle back around to problems.
Mm-hmm.
It's going to be that one. But anyhow, thank you very much.
Yes,
I appreciate it.
Thank you for coming. Good luck.
Thank you. We'll see you next week.
Yes, I'll see you next week. All right. Other questions?
Not off the top, like I said, I didn't do the practice exam.
Oh, you're good. Yeah, I would just say that practice exams are generally a really great way to like figure out exactly what's going on. Like I've said, I've noticed some wonky things with some of the limits, which have been stressing me out. But overall, I think they're a really great way to practice. Is there like a type of problem that you want to go over? We could look for one in.
What are the wonky things that are going on other than that sine of x over x?
That was the wonky thing that was going on.
Okay.
It just really kind of shook me because I spent a while trying to figure out how they wanted you to do that, and I got nowhere because there really isn't anywhere to go. Yeah. let's maybe do a couple of those limits, if that's okay with you.
Yeah, I got a limit. Well, it's a limit problem. A limit of x to 0, and it's going to be x to the 4th cosine of x over sine to the 4th over 3x. Or not over, it's just times 3x.
Sine to the 4th x, 3x?
Yeah, you just had it right. Sine to the 4th, 3x.
Okay. Where is this? This is this on one of the practice exams?
Actually, it was somewhere where I ended up taking a picture of it because I have a guy at work that he used to be a TA, and he kind of helps me out when I have questions.
For sure. Okay. So, the issue here, first of all, whenever I see a limit, the first thing I try to do is just solve it outright. If I can send, and the structure that I usually do is I say, if x is approaching 0, then this is approaching 0 to the 4th times cos 0 over, and this one is approaching sine to the 4th of 0, right? So this will be 0 because I have 0 times, this looks like theta, I'm sorry. That's a 0. So I'll have 0 times cos 0, which is 1. And then sine 0 is going to be 0. So I end up with something of the form 0 over 0, which is not something I can deal with. So the method that we have in this class is if we end up with 0 over 0, then we need to find some way to simplify that down and turn it into something that we can work with. So mostly this is just messing around with like trig functions and like equalities. So how would you start maybe breaking this down? Do you have any ideas in how to simplify it?
Have like the chain rule and the quotient rule put together.
Well, we're not taking a derivative. We're just taking a limit, right? So we don't have to worry about taking a derivative of this. We only have to worry about how to simplify this, right?
Yes.
Which is good, because then we don't have to worry about all of that. So maybe what's like an identity that you would want to start using to simplify this down?
I'm lost.
So for instance, I could say that I know it's true that sine squared x plus cos squared x is equal to 1. So I know that sine squared x is equal to 1 minus cos squared x. So I'm not, like, this is just me brainstorming because I'm not entirely sure right off the bat how to solve this problem. So this would be cos x over 1 minus cos squared 3x squared, right? Because this is equal to sine squared 3x squared.
Yeah.
So I'm kind of trying to frame this in a way that I could maybe cancel something out, but that doesn't look like it's gonna be a great idea. So instead of doing that, let's not do that. We can break this up. We can call this x. Oh, but they have, this is correct, right? This is sine to the 4th of 3x and cos of x up top.
Yeah, it's I don't have parentheses around the 3x.
Okay, but it is the sine of 3x.
Yeah.
Okay. Because if it was the sine of x, then we could cancel that out more easily. And it's not the cosine of 3x, it's just the cosine of x. Right?
Yes.
Okay. Okay. All right. So I'm just going to kind of brainstorm a little bit. Can't simplify it like that. There's a way that I would solve this problem that you guys haven't learned yet. So I'm trying to, again, think of a way around that. Because is this a problem that was given to you in this course, or is this like a practice problem that you found elsewhere?
No, I think this was on the homework that Web assigned.
Oh, lordy, Web assign. Okay. So okay. Give me just a sec.
All right.
Okay. There has got to be an easier way. This cannot be.
We
Okay.
simplify it to, well, it can't be secant. Well, not
Yeah,
cotangent.
usually the best way to simplify it is to just put it in terms of cosine and sine and then like see what happens. Like, so if it was like cosecants and secants and stuff like that, the first thing I would do is try to write it in terms of sine and cosine, because I can work with those a lot easier, or like know them a lot better, you know?
Yeah.
But this can't even. Oh. Okay, no small angles.
We could move on to a different problem. If you...
Yeah, we might need to do that because I don't know how they expected you to do this. This was on the homework? Damn. Okay.
It's like, and I couldn't get it figured out. And I think I just left it blank on my homework because I had no idea like how to do it.
You know what? I'll probably ask about this. I've got to talk with some other people anyway regarding that sine x over x thing. So I might just be missing like one of the techniques that we used, I guess. I don't know what it would be, but if that's the case, can I get your email, by the way? You can just go ahead and put it in the chat, and I can email you when I figure out what they want you to do with this. When are you taking the exam?
Tomorrow at 7:30.
Okay. Yeah, if you stick your email in the chat, I'll ask and get it.
Yeah, I have a couple other problems. There's one that was on one of the quizzes. It was the limit. It was f of x equals square root of 1 minus x over 1 plus x.
So was it a limit? You said?
Yes.
Limit of what?
Square root of 1 minus x over 1 plus x. It was fairly simple, but still tripped me up because it was like you had to do both rules, or the chain rule and the quotient rule. Okay.
Well, again, because we're taking a limit, we don't need to take the derivative here, right?
Well, I keep on getting them confused.
Yep. So with limits, our only goal is to simplify. If we were to want to take the derivative of this, then we would use, and is this what it looks like?
Yeah.
Okay.
That's not the derivative. It was find the limit of the function f of x equals square root of 1 minus x, 1 plus x. So I wrote it down as the first one you have up,
okay.
Limit.
Okay. And what is the limit going to?
0.
Okay. Okay. So, first things first, if we have a situation like this, right, and x is going to 0, then the first thing I do is I replace x with 0, right? Because we're saying that like x is getting really, really close to 0, and I just want to see what it does when it hits 0, basically. So if x is equal to 0, then we have this. The square root of 1 minus 0 over 1 plus 0, right? So this turns into the square root of 1 over 1, not 0, 1, which is the square root of 1, which is 1. So I do these little lines to say that this is like my next step. So if x is approaching 0, then here I have x approaching 0. X is approaching 0, which means this top is approaching 1, which means, and then the bottom is also going to be approaching 1, and so we end up with the square root of 1 is equal to 1. Does that make sense?
Okay, I think I was just getting, I think I was just getting confused with doing derivatives and limits like back to back. I keep on thinking.
Yeah. Fortunately, you've always got that limit right there just to tell you if you don't see the thing that says limit, just don't worry about the limits. And if you see limits, don't think about derivatives at that moment. Because what we established earlier, we had a problem where we had a problem where we had, if you remember the very first problem we did, it was like the cos of pi over 3 plus h, right? And we said that the definition of a derivative is this, right? Yes. And we like have gone over this like in this class basically about like how to like establish like what a derivative is, and like what it means to be like tangent to the curve and all of that jazz. But this problem that we did earlier was like very explicitly stating like this is equal to f prime of x, which is, you know, df dx. And so we have a variety of different ways of writing down what a derivative is. So if you see something that's directly in this form that gives you like h's and gives you like x plus h and then x, and you like it's very obvious, then you can start thinking about like what it means to be like a derivative like this. But if they give you something that's just like straightforward, like the limit is x goes to 0 of, you know, or the limit of x goes to 25 of root x over 5, or root x minus 5 over x minus 25. Like this should not make you think of a derivative because it isn't in that bottom, that blue form, and it isn't really
on like that. On that problem, you're just thinking algebra because it's going to be 0 over 0, which then you have a problem and you have to try to rearrange it for it to be not 0.
So how would you rearrange this one, for instance, if we had this limit? This is kind of like a common strategy. If you have like a radical, what you can do is like rationalize it. So multiply it by like the minus, like, so if I have positive root x minus 5 into negative root x minus 5, because when I multiply these together and I FOIL them, I'm going to end up with something that cancels. And I'm going to be able to, here. So I'm going to multiply this by 1. I can show you kind of how this works, right? So I can do this because this is the same thing over the same thing, and so it's 1. And so I'll end up with, I'm going to FOIL this first part, and I'll end up with negative x squared plus root x times 5 minus root x times 5 plus 25 over x minus 25, or this isn't x squared, this is root x squared, excuse me, x minus 25 times negative root x minus 5. So I'm just going to straight multiply that. I'm not going to distribute or FOIL. So I can simplify this. You can just pretend that I'm looping it around. So I'll end up with the negative square root of this, the negative square of the square root of x is just going to be x, negative x. These are going to cancel because they're plus 5 root x and then minus 5 root x, plus 25 over the denominator, which I'm just going to call it just like the same thing. Right? So this is going to be minus 1 times x minus 25. I'm going to like factor out a negative 1 here. And then I'm going to have my denominator, which is x minus 25, and then minus root x minus 5. So these are going to cancel. And I'm going to end up with negative 1 over negative root x minus 5. And so what I can do is just multiply this whole thing by negative 1, and I can end up with the limit of, so times negative 1 over negative 1. The limit as x goes to 25 of 1 over root x plus 5, right? Because this will be distributed, so it'll be a plus, plus, and a plus. All the signs get changed. So now, when I put this in, right, I can say that this is going to be 1, and then this is going to be root 25 plus 5. So it'll be 1 over 5 plus 5, which is going to be 1 over 10. And that's going to be my answer. So this is kind of rationalizing. Okay. This is like called rationalizing.
Now, to get, when you're getting rid of the radical and you times it by negative square root of x, that wouldn't be plus 5? You kept it as minus 5?
Yeah. So the reason I did that was because I wanted to be able to cancel these out right here. My goal was to make something that I could cancel out the internal sequence to. So I would end up with just a regular x, right? Because I'm going to rewrite this. So this would be, this first one is going to be minus 5 times minus root x. So it'll be minus 5 or plus 5 root x, because a minus times a minus. And then this last one is going to be the outside, so positive root x. And then I have to have that negative 5 there. They have to be different signs, so that it'll cancel.
Could you have done this problem the other way, just had times it by root x plus 5, and which would still cancel out the middle?
Yeah.
But it would give you...
Yeah, for sure. That should have worked.
So therefore, at the end, you wouldn't have to multiply it by the negative 1.
Yep. That would have also worked.
Okay. Usually radicals, you'll try to get rid of them by the FOIL method.
Yeah. I mean, if you see something that's very clearly in this form where you have this like root x minus 5, and you know that if you multiply it by this slightly, like this really similar, like it's pretty easy to see that x is root x squared, and then 5 is 5 squared is going to be 25. And so this is a really good way of like recognizing and like solving by like selectively picking what you're multiplying by, so that you can FOIL it out and end up with something that cancels. Because the ultimate goal was to end up with this step right here, where I could cancel out that x minus 25 from the bottom. So I made it into something that I could work with better.
I just have 2 more problems now that I'm reviewing.
Sure.
If you have time.
For sure.
I got limit of h to 0. And this is going to be the formula f of x plus h minus. It's going to be that. So it's going to be tan, then parentheses pi over 3 plus h parentheses minus tan of pi over 3 all over h.
Okay. So we did a problem really similar to this at the beginning.
It was the cosine of this.
Do you remember how we solved it?
Yeah, this is the one you were saying, this is the definition of a derivative.
Right?
So
this is going to be f prime of x, or f prime of pi over 3. Right? So we know that the limit as h goes to 0 of f of x plus h minus f of x over h is equal to f prime of x. So we know that our x is going to equal pi over 3. And what is going to be f of x, the function?
That would be the tan of x.
Mm-hmm. So
therefore, secant squared.
yes.
You're taking derivative of x, secant squared of pi over 3.
Wait, sorry, lush. Okay, so you said f prime of x is going to be the secant squared of x, and then yes, so f prime of pi over 3 is going to be the secant squared of pi over 3. Oh no. Yes, that's correct.
So secant is 1 over cosine, and 1/3 of pi, that's going to be 1/2 under 1, so it'd be 2. Doing it all in my head, so 2 squared,
Yeah.
right? So 4.
So I'm going to split this up a little bit. Cosine of pi over 3 is cosine of pi over 3. This is one of the 30, 60, 90, I think. I think it's going to be 1/2. I think you're right. No?
Yeah.
Adjacent? Oh, but it would be adjacent to the...
So cosine pi over 3, that should be 1/2, right? I believe. So you got 1 over 1/2.
I think so. Yeah. I just Googled it. Yes. Sorry. I don't have my trig functions really memorized anymore. I know. I'm so sorry. So this is 1 over 1/2 times 1 over 1/2, which is 2 times 2, which is 4. So if f prime of pi over 3 is equal to 4, and this limit is equal to f prime of pi over 3, then this limit is also equal to 4. And that's how you find this answer.
Okay, so the only time that derivatives and limits coincide is when it's written in this formula.
That if you're like just solving like brute force solving a problem, this is when you combine, you're taking a derivative with the limit, right? The limits and the derivatives like coincide like conceptually speaking, but in terms of problem solving, this is where you're going to use them both to solve the problem together. Does that make sense? Because I don't want to say that they don't coincide, because they definitely do. They're intrinsically like related to, like, definition wise. It's very important that you recognize what this definition like means for finding a derivative. Or means like to define a derivative, but in terms of problem solving, you don't need to worry about taking like derivatives while you're taking a limit, unless it's of this form.
Okay.
That was a very roundabout way, and I'm kind of saying that in order to like, so I phrased it the way that I did because I don't want you to think that they're not related, but yes. Problem solving wise, this is the only time you're going to kind of combine the two types of problems. So.
Okay. And the other one is just a derivative. I'm taking a derivative of f of x is equal to parentheses 1 plus x squared over x minus, or 1 minus x squared, parentheses to 17th power.
Yep. This? Is this what we're looking at?
Yes.
Okay. What is
so
the
you
first?
do outside function, inside function, right?
Mhm. Yep. So I would write this as the function f of g is equal to g to the 17, where g of x is equal to 1 plus x squared over 1 minus x squared. Does that make sense?
Yes.
So now I've defined it as exactly what the outer function is and what the inner function is. So my f prime of g is going to be 17g to the 16.
Mm-hmm.
And then my g prime of x, I'm going to need to use what for?
High-D low, low-D high.
Yep, basically.
The quotient rule, right?
Yep, so we're going to use the quotient
So
rule.
1 plus x, then the derivative of.
I'm sorry, I'm
2x.
like, I write everything out. So I would say that this is hx over jx, where hx is equal to 1 plus x squared, and jx is equal to 1 minus x squared. So h prime of x is equal to 2x. J prime of x is equal to negative 2x. And the reason I write everything out is because I'm really always very concerned I'm going to miss something like a negative sign, which I do very frequently if I do it in my head. So I know that my quotient rule is going to be what? It's going to be h times j prime minus h prime times j.
Yeah.
No, it's reversed.
Over.
Yeah, it's reversed, right?
Well, it's
H prime is first.
No.
Oh, you're right. Sorry. Oh, should know this.
Yeah, the little high-D low, low-D high.
Yeah. Over j squared. So if I put it together, then I've got h times j prime minus j times h prime over j squared, x squared again. So I'm going to actually distribute all of this. It'll be negative 2x minus 2x cubed minus 2x minus 2x cubed. So it'll be minus 2x minus 2x cubed minus 2x plus 2x cubed. So these are going to cancel, and all of this is over minus 1 over 1 minus x squared. So I have minus 4x over 1 minus x squared, right?
Yes, I believe. Would you square that bottom to simplify it more, or?
Nope, I have to square the j. Yeah, in the bottom.
Just have
yeah.
1 minus x squared times. Or would you just leave it as that?
I would leave it like this. In my experience, it doesn't really help to distribute and FOIL, and it just makes things a little bit messier. So I would leave it like this. Okay. So we use the quotient rule to figure out what g prime would be. So we can go ahead and put all of this together to find the derivative of f. So it would be f prime of x is equal to f prime of g, which is going to be 17, and then g is equal to 1 plus x squared over 1 minus x squared, and then that's to the 16th. Times g prime, which will be negative 4 over x time negative 4 over x over 1 minus x squared squared. So this is going to be
a mess.
Oh, I mean, it's not, you're not going to simplify it too much. So it'll be negative 68, so 4 times 17x over 1 minus x squared squared times, or just parentheses, 1 plus x squared over 1 minus x squared to the 16th. And that's my answer. Does that make sense?
So you times the negative 4x by the 17th because it's 17 over 1. And then the denominator you
Yep,
kept
so
that.
I basically just moved, like if I had that 17 there, it doesn't really matter where the 17 is because they're all multiplied by one another, right?
Okay,
So
yes.
I could just say that this is times 17. And so this would, I'm getting rid of this 17 then. And that would be 17 over 1. So it'd be 17 times the numerator and the denominators. And so if this denominator is 1, then it's just the same denominator.
Okay, yeah, that makes sense. It's just so, like, rearranging it like that is.
Yeah, the only reason I did that was so that I could stick these two numbers together, the 4 and the 17. Because, I mean, leaving it as 17 times this first answer in the blue is technically fine. It's just typically they prefer putting it as the bottom one because it's a little bit more concise.
Okay. I believe that's all other than reviewing first, second, third week's limits.
Yeah, it's the limits that really sneak up on you. So that is definitely like just practice problems. I will get back to you about that one problem. I wrote it down. I'm going to try to figure out what's going on. And I will, I'll upload this video probably like tomorrow morning. So I'll include a piece either in the description of the video or like maybe like an extra like tag on the end of it of a video that covers what is happening with that one problem that you found. So yeah, that's what I got for you.
Okay.
I hope that the exam goes spectacularly for you. And I wish you all of the luck in the world. I believe in you.
The only thing that creeps up on me is the time because it takes me time to figure out each problem. I usually run out of time before I can get all the problems done.
That's a mood. That's definitely, yeah, I know that feeling. So,
yeah, it kind of sucks. It's like I know how to do these problems, but I don't have enough time to do the problem.
Yeah, I actually just had a physics exam where that was basically like my life. So it was.
Which physics?
212.
Okay, I'm taking that probably over the summer.
Yeah, it was, you know, it's just, you know what you're doing. You just gotta move fast enough to beat the clock. So I wish you all of the luck in the world on that. Because I know how stressful it can be. So, yeah, I hope you have a great evening.
Yep, you too.
Yep.
Thank you.
I will see you around. Thank you for coming.